PhD Tony to Sleeping Warrior. There is no force acting on the balls in Blue Marble Science's experiment. Yet you say there is, yet you cannot name that force because gravity isn't a force, is it, in mainstream science anymore? So, yeah, there is no force acting on your balls.
Taking a comment Tony made out of context. What he says and what I say are exactly the same thing.
So when you say and calculate the force on your balls and PhD Tony says there's no force on your balls, you are telling me you are saying the same thing?
We know what causes gravity. Gravity is the bending of space-time.
Because it just blew my mind that we didn't know what most of the universe was made of, and that all the astronomy we'd been doing forever was based on an incorrect assumption, a natural assumption, but an incorrect one. And then when I realized that we don't know what gravity is, I thought, well, there's something there too, because we don't, we just, we take it for granted. And with good reason. With good reason, we thought that astronomy was the science of the visible universe, because what else were we going to think? And the same thing with gravity. And I found a lot in researching the book that when I would tell people, we don't know what gravity is, people who weren't scientists would say, well, what do you mean? We do know what it is. If I let go of this thing, it'll fall, and so on. And but when I would say it to physicists, they would say, "Yeah, that's right. We don't know what it is." And I just love that disconnect, between what our common assumptions are and what's really out there. So
we know what causes gravity. Gravity is the bending of space-time.
In researching the book, that when I would tell people, we don't know what gravity is, people who weren't scientists would say, well, what do you mean? We do know what it is. If I let go of this thing, it'll fall, and so on. And but when I would say it to physicists, they would say, yeah, that's right. We don't know what it is. And I just love that disconnect, and so on. And but when I would say it to physicists, they would say, yeah, that's right. We don't know what it is.
We know what causes gravity. Gravity is the bending of space-time.
Like what it is? I don't know.
Planck era, if you want to go look that up. And the really most important thing to understand is that gravity showed up really quickly, and it's a property of all matter. But what causes it? Why did it show up just then? Shrug. We don't really know. This is about all we know so far. The thing is, we're trying to describe as much of gravity as we can. So without knowing all the pieces, we're going to get some stuff wrong. And that is why Newton was wrong with the law of universal gravitation.
It acts exactly like a force, and we can treat it exactly like a force. This is what Tony says in the comments to my video. It is entirely valid to treat gravity as a force in a terrestrial setting. Indeed, in most places in the solar system. Now pay attention to this part, Rachie. If you're going to say gravity is not a force, then you cannot then say the existence of an acceleration requires a force.
Actually, I can, because that's Newton's first law of motion, that an object at rest will remain at rest unless acted upon by a force. An object that is moving at a constant speed in a straight line will remain moving at a constant speed straight line unless acted upon by a force. So yes, I can say that, because that's Newton's law. Why do you always ignore Newton's first law?
Told us that d in your equation is the acceleration rate due to disequilibrium. You said it has a value of 9.81 meters per second per second. That's an acceleration. Then you said it is the fastest something falls in a vacuum without any resistance. That implies a velocity. I think you meant to say it's the fastest something accelerates in a vacuum without any resistance.
So if I drop a bowling ball in a vacuum and it accelerates down to the floor, is that not falling, Blue? Because right now you're saying that is not falling, so I don't know what that is to you, but the definition of that to me is it is falling and it is accelerating. It is one and the same. It is falling and accelerating. However, you are trying to say that it's accelerating but it's not falling. Weird.
Rachie, this is the definition of what we call little g. You just inserted the acceleration of gravity on Earth at sea level in a vacuum in your equation for disequilibrium. Let's listen to it again.
Disequilibrium rate of 9.81 meters per second, which is the fastest basically that something falls in a vacuum without any resistance kind of thing, with the minimal effects basically.
So you've replaced the acceleration of gravity that we call little g with d, which you call the acceleration rate due to disequilibrium, but you haven't told us how that works.
I have told you how that works. So basically the density of the object and the density of the medium have to have a difference. They have to have a relative density difference between them. And if they are not the same, then you will get an acceleration. And more dense than the medium will go down, less dense than the medium will go up. And if you want to find the fastest rate of disequilibrium, so the fastest acceleration that this force can imply, then you put it in a vacuum because you're taking away the majority of the medium, so there's basically nothing in there, so it's basically a vacuum. And then basically you see how fast it falls, because it can't rise because it's not less dense than a vacuum, so it has to fall. So it goes down because it's more dense, and therefore it's falling and it's accelerating due to the force of disequilibrium because it's not in equilibrium. So disequilibrium basically just means the uneven distribution of mass, so they're not the same. So yeah, you put it in a vacuum, you see how fast it falls, and that is the fastest that it can fall in a vacuum. So that's the fastest downward acceleration that you can basically get.
You know, it's exactly the same as little g according to your description. So let's check out your formula. What you've said over there is that the density of an object times its volume times the acceleration of gravity minus the density of the medium it's in times the volume of that medium the object is displacing multiplied by the acceleration of gravity will give us net weight. Okay, no problem with that. Remember that density times volume is actually mass. So what you're saying is net weight is equal to the mass of the object times acceleration of gravity minus the mass of the medium that the object is displacing times the acceleration of gravity. In other words, net weight is the weight of the object minus the weight of the medium it displaces. Richie, this is Archimedes' principle. We've known about this for the better part of 2,300 years now. This is exactly how this works. What you haven't done is tell us what causes this acceleration rate due to disequilibrium.
Yes, that is Archimedes' principle. Unfortunately, you have a problem with Archimedes' principle now, don't you? Let's run through it. So you say that net weight equals the density of the object times volume times gravitational acceleration, 9.81 meters per second, right? Minus the density of the medium times the volume displaced times, again, 9.81 meters per second. Okay, fine, let's use Archimedes' principle. I am holding an object. Let's say the density of the object is 10 kilogram meters cubed, and its volume is 2 meters cubed, so its mass is 20 kg. So its weight is 196.2 newtons. The object is in air, which has a density of 1.2 kilogram meters cubed. Now, when I let go of that brick, it is weightless, right? It's falling as it's denser than 1.2 kilogram meters cubed of the medium, and things that fall are weightless. So therefore, the object has no weight, right? Things that fall are denser than the medium. The object is denser than the medium, so therefore falling. Weight, according to PhD Tony, is the force required to stop an object from falling. Remember, when they are falling, you lot say they are weightless. So, I let go of this denser than air object. It's falling. It has no weight because it's falling. So, the weight of the object equals 0. The weight of the medium equals the density of the medium times the volume displaced times 9.81 meters per second. So, 1.2 kilogram meters cubed times 2 meters cubed equals 2.4 kilograms times 9.81 meters per second equals 23.544 newtons. So now net weight equals minus 23.544. Really, Blue? So the object has no weight and now has negative weight, so should rise. The weight of the medium is 23.544 newtons and the weight of the object is 0. So the medium should get pulled down more and the object rise as it's weightless because it's falling. The object has no weight. This also means that objects that are falling are weightless, so objects that are rising or not falling have a weight. And yet falling is meant to be a product of weight. If everything was weightless, remember, they would just float. It's weight that is meant to give direction. So here, from NASA apparently, it says weight is a force, and a force is a vector quantity having both magnitude and a direction associated with it. In flight, the airplane rotates around the centre of gravity, but the direction of the weight force always remains towards the centre of the Earth. Whoops, it looks like PhD Tony and NASA need a word with each other, because PhD Tony says that weight is an upwards force. Whoops. So let's say I have an object 10 kilogram meters cubed, volume 4 meters cubed, so its mass is 40 kilograms. I drop it off a cliff, it's falling, therefore it's weightless. No force is acting on the falling object. So all we have is the upwards force from the air, or the buoyant force as you would call it. So the buoyant force equals the density of the medium times g times v. So 1.2 kg meters cubed times 9.81 meters per second times 4 meters cubed equals 47 newtons. So the object should have 47 newtons of buoyancy force in the upwards direction and no force in the downwards direction. Therefore, again, the direction the object should travel is upwards, as the only force acting on it is the buoyant force, which is in the upwards direction. However, if you don't want the force, you don't want the weight, and all you want is the acceleration, there is a simpler way. Then we can do the density of the object minus density of the medium times disequilibrium rate in a vacuum divided by density of the object, and that will again give you the acceleration rate.
Okay, well, let's remember that d in Rachel's world is actually what we call little g. Rachel, you got a small problem with your formula. Remember this thing we call Pemdas? You evaluate stuff in the parentheses first, then exponents, then multiply, then divide, then add, and then subtract. You needed to put some parentheses right here, otherwise you're going to get a really wrong answer. But
no, otherwise you're going to get a really wrong answer. Because I did actually put the brackets in there earlier, but I'm not going to keep doing it every time. I mean, come on, you know what I mean? It doesn't really need to be done every time. Once you've seen it once, you know exactly what I mean, right? And when I'm telling you that you do the density of the object minus the density of the medium times the disequilibrium rate divided by the density of the object, I literally mean in that order that I said it to do it in. So, yeah, brackets or no brackets. Doesn't really matter. What I told you to do it is the way that I told you to do it, which is the density of the object minus the density of the medium times the disequilibrium rate divided by the density of the object. But anyway, I did put brackets in there earlier, so now you're just basically being picky, because you know I put brackets in there, don't you? I just didn't this time. I don't always put meters per second in every time either. You know, I kind of expect people to know what I mean, but I guess that's a bit too much expectation of people, right? So here you can see that I did put the brackets in, you know what I mean? So, yeah, like I said, you're just being picky on that one, really.
the parentheses in there, that expression, you get a net acceleration. No problem with that. Okay. The real question, Rachie, is where did little d come from? Where did g come from? That's the question.
And I've told you where little d comes from. Well, where d comes from. It's from in a vacuum, the rate of fall in a vacuum. So things accelerate fall at 9.81 meters per second squared in a vacuum. So, like, that's the disequilibrium rate. I've already told you in this. I don't know really how many times I have to go over it. Basically, the uneven distribution of mass causes an acceleration because the density of the medium is not the same density as the object because the uneven distribution of mass. Basically, that causes an acceleration. And the acceleration rate in a vacuum, without any resistance to the medium and pressure and all the other factors that factor into the acceleration rate that changes it, you know, they're not there anymore. So therefore, that you're left with pretty much essentially the acceleration due to disequilibrium. And that's where it comes from, in a vacuum. Unless you want to deny that things in a vacuum fall at 9.81 meters per second squared. In which case, I'd love to see some proof of that. Go ahead. So as we can see from the formula for acceleration equals density of the object minus density of the medium times by the disequilibrium rate, 9.81, divided by the density of the object. That is all to do with density of the object, density of the medium, and disequilibrium. Absolutely nothing to do with mass, volume, or gravity. In fact, it is only relative density that gives the acceleration, and this is how we prove it.
What do you mean it has nothing to do with mass, volume, or gravity? Rachie, density is mass per unit volume, and d in your equation is the acceleration of gravity, little g.
Yes, the density is mass per unit volume. But the problem is density is not mass, is it? It's mass per unit volume. It's not mass. See, when I first came into this, and I first started looking into things and questioning gravity and questioning all the different things, I was saying basically mass and density are pretty much the same thing. Like, density is mass per unit volume. That it is essentially mass, because it's mass per unit volume. And that's what I was saying when I came along, which sounds like basically what you're saying right now. But it's not, is it? Because I didn't use the mass of the object, did I? If I, for instance, wanted to use your density, are you going to give me your mass? So if I asked you for your density, are you going to give me the mass of yourself? Of course you're not. If I asked you for the density of a bowling ball, are you going to give me the mass of the bowling ball to use in my equation? Of course not. If I asked you for the density of a cruise ship, are you going to give me the mass that I need to use in the equation for the cruise ship? Of course you're not, because I need to use the density. So if I use the density, then it's not the mass, is it? Again, if I asked you for your density of your body, are you going to give me the mass of your body? No, you're not, am you? Because density and mass are not the same thing. And I didn't use mass. I used density. As for the d and g thing, again, d is just the acceleration rate in a vacuum where the object is not the same density as the medium. Therefore, you get an acceleration rate. And because everything is more dense than a vacuum, everything's pretty much going to fall in a vacuum. So, yeah, that's where the acceleration rate of d comes from the object being denser than the medium, and from the least medium that you can get. So a vacuum is essentially the less medium that you can get. You can't get perfect vacuum, but essentially it's taking away most of the other factors and effects. So, yeah, that's where it comes from. I also did not use the total volume of the object either, and that's what I meant by volume. The total volume of the object wasn't a consideration, neither was the total mass of the object. That's what I'm saying. I didn't use mass, I didn't use volume, and I didn't use gravity. You could say I used gravity by using 9.81 meters per second, but you're going to have to prove that that is gravity, which you cannot really do, can you? But we can prove it from disequilibrium easily. So, as we have done many times, experimentally, it's fine, it's verified, But you can't do that with gravity. Anyway, so yeah, I didn't use the mass of the object, and I didn't use the total volume of the object. Therefore, I didn't use the mass of the object, and I didn't use the volume of the object. All I used was the density of the object, which, again, is mass per unit volume. It doesn't tell you how much mass is in that object, and it doesn't tell you how much volume that object takes up, does it? So I didn't use the mass, and I didn't use the volume. That's exactly what I meant. Again, if I wanted to use your density, did I use your whole volume? No, I didn't. Did I use your whole mass? No, I didn't. So therefore, I didn't use your mass, did I? And I didn't use your volume, did I? I used your density. I didn't use the number that would be your total mass, and I didn't use the number that would be your total volume. Therefore, what I'm saying is I didn't use your mass and I didn't use your volume. I used your density. Because that's what I did. I used density. Didn't use mass, didn't use volume of the object. Didn't use mass of the object, didn't use the volume of the object. All I used was the density.
In your words, you said you can't have an acceleration without a force. You claim that little d in your equation is an acceleration, so what force is acting on the object to produce the acceleration, and where is that force coming from?
Sure. So, you can't have acceleration without a force, Newton's first law. I didn't actually say that. That's Newton's law. So that's not my own words, is it? That's Newton's first law, that you cannot have an acceleration without a force. That an object at rest will remain at rest unless acted upon by a force. It will not accelerate unless acted upon by force. That an object moving at constant speed in a straight line will continue moving at constant speed in a straight line unless acted upon by a force. Constant speed. So again, you can't have acceleration unless acted upon by a force. That is not my own words. That is Newton's law, which you always fail to address. Why? Why do you always fail to address this, Blue? I really don't understand it. Like, you could easily just address this and have it over and done with. So could have FTFE and yourself when we was on the debate thing. But you don't want to address that. And you don't even want to say that it's Newton's laws. Now you're trying to say it's my own words. No, that's Newton's law. I don't understand why none of you will address Newton's first law. Like, what is wrong with you? As for the force comes from RDD, so relative density disequilibrium. So you have a disequilibrium, an uneven distribution of mass. So the density of the medium is not the same as the density of the object, and therefore an acceleration arises. This is why if you have the density of the medium and the density of the object the exact same, it will neither rise nor fall, because it's in equilibrium. So the only way to get anything to accelerate, to rise or fall, is to put it in disequilibrium, to have the mass unevenly distributed. So that's where the force comes from. So the uneven distribution of mass, the disequilibrium, basically causes an acceleration rate. And the direction is down for that. But only if the object is more dense. If the object is less dense than the medium, then the object will rise. So it gives you both a magnitude and a direction, but it's all dependent on whether the object is more dense or less dense than the medium. That will give you the direction. And the acceleration rate comes from the uneven distribution of mass, aka disequilibrium. So there's your magnitude and there's your direction, and it comes from RDD. That is the force. Now, how about you answer what force moved your balls blue? Because you still haven't answered that under Newton's first law, have you? And you can't answer it under Newton's first law, can you? Because there is no force. So, what force moved your balls blue? And this is why you always ignore Newton's first law, and I really don't know why. Like, if you want to say it's wrong, fair enough, go ahead and say it's wrong, but you're not even saying it's wrong. So, what is it? If it's right, then there has to be a force moving your balls. So, it's either right or it's wrong, blue. Which one is it? So, the medium and the object's density were the same, and I will even give you 9.81 as gravity for a moment to prove a point. 10 kilogram meters cubed minus 10 kilogram meters cubed equals 0 kilograms meters cubed times 9.81 equals 0 meters per second. Oh look, no acceleration. Why is that? Because there is no difference between the object's density and the medium's density. Therefore, no disequilibrium. The relative density of the two are the same, and thus the acceleration rate is 0. Again, proving it's all to do with the density of the object and the density of the medium, aka relative density or differential density, or whatever you want to call it. But basically, the relative density, so one density relative to another density. So just how left can be relative to right, it's one density relative to another density. So again, proving that it's the density of the object relative to the density of the medium that actually causes the acceleration.
What you just said is one of the most insanely idiotic things I have ever heard. At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
So how does relative density disequilibrium produce a force, Rachie? How does the density of an object, and that alone, produce any sort of force? On the other hand, we can use Newton's law of universal gravitation and easily see where the force comes from, and it's totally appropriate to do that. As PhD Tony said, it is entirely valid to treat gravity as a force in a terrestrial setting. Now for fun, let's do this.
So I noticed that all you did was do some face palms and didn't actually address the point. So how about we go back to the point and you actually address it this time? Again, if the medium and the object's density is exactly the same, and I even give you any acceleration rate you want, 9.81, 10, 100, 25, whatever acceleration rate you want. If the density of the object is the same as the density of the medium, there will be no acceleration. No matter what acceleration rate you want to give gravity, or I want to give disequilibrium, because there is no disequilibrium. Therefore, the acceleration rate due to disequilibrium is 0. 0 meters per second, because it's not in disequilibrium. Therefore, there is no acceleration rate. There is no direction, because it's exactly the same. The density of the medium is exactly the same as the density of the object, therefore no acceleration. So that's why it will neither rise nor fall, and yet you totally just facepalmed this and went over it and didn't actually address the point. So do you disagree with that? So what's wrong about it? You're saying everybody here is stupid for having listened to it. Okay, So if I have a density of an object and a density of the medium exactly the same, is it going to rise or fall? Even with your 9.81 meters per second squared. No, it's not, is it? Like I said, you can put that number as anything you want right now. It doesn't change the fact that that object is neither going up nor down. You can make that 9.81 as strong as you want. Let's say it's gravity, and you can make it as strong as you want. So you can make it 1,000 meters per second. Again, because the object's density is the same as the medium's density, it's neither rising nor falling because they're the same. And there is no disequilibrium rate. Therefore, the 9.81 meters per second is actually zero because it's not in disequilibrium anymore. And that's why it doesn't go up or down. And yet you just want to skim me past that point and use a silly clip instead of actually addressing the point. Shocking. So equilibrium in physics, the condition of a system when neither its state of motion nor its internal energy state tends to change with time. So equilibrium, its state of motion doesn't change with time. So disequilibrium would be the opposite, wouldn't it? So disequilibrium is when its state of motion tends to change with time. Therefore, disequilibrium is a force that causes an acceleration, aka RDD. So you say PhD Tony says it's entirely valid to treat gravity as a force in a terrestrial setting. Okay. No, it's not though, is it? If it's not a force, it's not okay to treat it as a force. It's like my daughter pretended to be a dinosaur, and me saying, oh, because she's pretending to be a dinosaur, therefore I must treat her like a dinosaur. I must act like she actually is a dinosaur. I must feed a dinosaur food. I must run away from her, especially if she's a T-Rex and she's going to eat me. I must be absolutely petrified and act like she's an actual dinosaur. And I must actually be running for my life because I actually have to act like she's a dinosaur because she's acting like one. No, she's not a dinosaur, is she? Even if she acts like one. She's not one. Therefore, we can't treat her as one. We can pretend she's one if we want, sure. But it's not the same as her actually being one, is it? So, you saying gravity you can treat as a force, it's not actually a force, is it? So therefore you can't actually treat it as a force because it's not a force anymore, thanks to Einstein. And actually I won't go to PhD Tony for your information, to be quite honest, as even Globers are denying what PhD Tony is saying there. There's actually a Glober in your comment section on the video you mirrored who's having a back and forth with PhD Tony. It's about 128 comments in, I believe. And they're having a back and forth anyway. And even he's realised that PhD Tony does not know what he's talking about when it comes to gravity. So, yeah. It's not just flat earthers who disagree. It's also Globers who disagree with what PhD Tony is saying as well. So, yeah. Guess he's wrong, isn't he? Because what do you say? If everybody else is against you, if everybody else is telling you you're wrong, then you must be wrong, right? Well, you've got Globers and flat earthers telling him he's wrong, so he must be wrong, right? Then he goes on to say, if you're going to say gravity is not a force, you cannot then say the existence of acceleration requires a force. Again, that is Newton's first law. An object at rest will remain at rest unless acted upon by a force. Therefore, it will not accelerate unless acted upon by a force. Newton's first law. An object moving at constant speed in a straight line will remain moving at constant speed in a straight line unless acted upon by a force. Again, that's Newton's law. Basically, it will move at constant speed. That's not an acceleration, is it? So, it'll move at constant speed unless acted upon by a force, Newton's first law. Therefore, no, you cannot say you can treat it as a force if it's not a force, because there will not be any acceleration without a force according to Newton's first law, which you, PhD Tony, FTFE, and all of you, well, most of you Globers, ignore. So what is it? Again, is he right or is he wrong? Because that's Newton's first law, which you're all just basically ignoring.
On the other hand, we can use Newton's law of universal gravitation and easily see where the force comes from. And
you can use Newton's law of gravitation and easily see where the force comes from. Oh, that's a problem though, isn't it? Gravity's not a force anymore, so you can't see where the force comes from because there is no force. So how did you see where a force comes from when there is no force? So it's like saying, oh, I've seen a baby come from here, but there is no baby. Like, you've seen a force come from here, but there is no force. So, yeah, no, doesn't work.
now for fun, let's do this. 2 years ago, I measured the radius of the Earth to be 6,370,760 meters by doing the Eratosthenes method.
Okay, so you say you did the Eratosthenes method, which is basically shadows, and measured the radius of the Earth. So you must need at least 3 shadows. So you was in 3 places simultaneously, or you had help. Okay. Do you have evidence of this? And also, if you believe that you can tell the radius of Earth from shadows, like why? Because they change shadows, okay. But on a flat Earth, if you had a local sun and you move the sticks further and further away, you're going to get different length shadows. So I don't really see how that's proving anything. But being as though you think you can get the radius from shadows, if I took a ball outside in the sun and stuck some sticks on it, gave you the lengths of the sticks and the lengths of the shadows, etc., are you telling me that you could tell me the radius of that ball that I've stuck outside? If so, let's do it, because I really don't think you could. But I'm willing to do it and be proven wrong if that's the case, but I really don't think you can. So yeah, let's do that. If you're up for it, Blue, I'll take a ball outside, I'll stick some sticks on it, give you the measurements that you need, and then like you can tell me the radius of that ball. Yeah, are you up for that, Blue?
I ran the Cavendish experiment, and I measured an average specific gravity of the Earth to be 5.47.
You say you measured the average specific gravity to be 5.47. Okay, well, as far as I'm aware, unless you're on about something else, in which case you are, please clarify. But as far as I'm aware, specific gravity is basically relative density, right? One density divided by another density. So you did one density divided by another density, okay? So what was the densities that you was dividing, and where did you get those densities from? Yeah.
I also measured the universal gravitational constant to be 6.63 times 10 to the minus 11th Newton meter squared per kilogram squared.
Hold up, you missed the mass of the Earth off. So you've got the mass of the Earth. Where did you get the mass of the Earth from, Blue? Because in order to get the mass of the Earth, you're going to need the density of the Earth, and you're going to need the volume of the Earth, aren't you? So if you have the density, where did you get the density from? If you're using an average density, well, that's not really the mass, is it? Because the density changes from location to location, and just saying an average density is not really giving you the specific number for the mass, is it? Because you're not actually calculating it properly. All you're doing is using an average. So therefore, the mass could be less or more than what you are saying, because all you're doing is using an average, if that's the case. So yeah, please clarify how you got the mass of the Earth and how it is correct, because yeah, if you're using an average density, then it's going to be off because the density changes everywhere, in which case, no, you haven't got the mass. You say you measured big G. Okay, so can you tell me how you measured big G? Because according to Newton, big G is the proportionality constant connecting the gravitational force between the two bodies with the product of the masses and the inverse square of the distance. But for Einstein, in Einstein's field equations, it quantifies the relationship between the geometry of spacetime and the energy momentum tensor. So for Newton, basically, it was the product of their masses and the gravitational force between the bodies and the inverse of their distance. And for Einstein, it was the relationship between the geometry of spacetime and the energy momentum tensor. So, which one did you measure, and how do you know you measured that? How do you know that that was exactly what you measured? Can you tell me that?
If we plug those numbers into expression for acceleration, we get an expected acceleration for gravity, little g, of 9.68 meters per second per second. That predicted acceleration is within 1.3% of what we actually measure.
So what you're saying is the acceleration rate you got was wrong. Okay, so it wasn't 9.81, it was wrong that you got. And also, again, coming back to the mass of the Earth and everything. So you lot say that it changes from location to location. Okay, if it changes from location to location, like, I'm not talking about altitude at the minute, I'm just talking about different locations on the Earth. So if you say it changes at different locations on the Earth, well, what changed? If we keep the distance from the center the same, yeah, and we keep G is obviously going to be the same, right? So then the only thing left is mass. which means that the mass of the Earth must have changed in order to change the acceleration rate. So yeah, again, your formula does not work because the mass of the Earth didn't change, did it? Yet it changes from location to location, and like I said, if you keep the distance between the masses the same, and obviously g's kept the same, then obviously all you're left with is m, which is mass. So the mass of the Earth didn't change, did it? So yeah, your formula doesn't work, Blue. Sorry. I should say Newton's formula doesn't work. Sorry about that. And again, you don't have the mass if you're using an average density. You know, you don't have the mass.
So do this. Using relative density and relative density alone, predict the acceleration for gravity at sea level on the Earth. Until you do that, relative density disequilibrium is simply gravity with another name.
Sure, relative density disequilibrium. So acceleration equals density of the object minus density of the medium times disequilibrium rate divided by the density of the object. Therefore, in a vacuum, there is a disequilibrium rate because the object's not going to be the same density as a vacuum. Therefore, the rate of disequilibrium now enters the equation. So, 10 kg m3 minus 0 kg m3 times 9.81 meters per second divided by 10 kg m3 equals 9.81 meters per second. Done. So just to reiterate the point, if I have an object 10 kg m3 and a medium 10 kg m3, obviously you do the density of the object minus density of the medium equals 0 kg m3. 0 times anything is 0. Thus there is no acceleration. You can change that acceleration rate due to gravity that you say it is to anything you want. You can make it stronger, you can make it weaker. It doesn't matter because 0 times anything is 0. So therefore, there's no acceleration because the density of the object is the same as the density of the medium. Because there is no disequilibrium. Therefore, the disequilibrium rate then is basically 0 meters per second because there is no disequilibrium. So yeah, again, it's all to do with relative density and relative density disequilibrium. So if there's a disequilibrium, there will be an acceleration. If there's no disequilibrium, then there's no acceleration. It's as simple as that.